Hey everyone, and welcome. There's a set of rules that literally governs everything. I'm talking about the pot of water boiling on your stove, the engine in your car, even the chemical reactions that are keeping you alive right now. This is thermodynamics. It's like the ultimate rulebook for how energy and change work in our entire universe, and it's non-negotiable.
And hey, you don't have to take my word for it. The one and only Albert Einstein was absolutely convinced that thermodynamics is one of the most solid, unshakable pillars of all of science. I mean, think about that. This isn't just some passing theory, it's a foundational law of reality itself. So what can these amazing laws actually tell us? Let's find out.
Okay, so you might be thinking, why should I care about this? Well, here's why. Thermodynamics answers some of the biggest questions out there. Like, have you ever wondered, if you mix two chemicals together, what actually decides if they're going to react? Or why some things just happen while others don't? What gives a process its direction? In this explainer, we're going to unpack the exact tools that let us predict the course of nature itself.
All right, so here's our game plan. We'll start by defining the playing field. Then we'll jump into the first big law of energy. After that, we'll look at a super practical tool for chemists. Then talk about the arrow of time. It's the cool one. And finally, we'll get to the ultimate decider that pulls it all together. Let's get started.
All right, Section 1, defining the playing field. Before we can talk about energy changing, we have to be super clear about what we're actually looking at. So, in thermodynamics, the first thing we do is draw a sort of imaginary line in the sand, a boundary that separates the thing we're interested in from, well, everything else. So, the part we're focused on, we call that the system. It could be anything, really. A chemical reaction bubbling away in a beaker, a piston firing in an engine, or even a single living cell. And then, everything outside of that, everything that can interact with it, we call the surroundings. Simple enough, right? For our purposes, the system plus its surroundings, that's our entire universe.
Now, systems come in three main flavors, and it all depends on what they exchange with the outside world. First, you've got an open system. Think of a hot cup of chai. It lets out heat, that's energy, and it also lets out steam, which is matter. Makes sense, right? Then there's a closed system. Imagine a tightly sealed water bottle. It can get warm or cold, so it exchanges energy, but no water gets in or out. Finally, you have an isolated system. This is like a perfect thermos. Ideally, nothing gets in or out. No energy, no matter. And trust me, knowing which one you're dealing with is absolutely crucial for everything that follows.
Okay, so now that we've set our stage, let's dive into Section 2, the first law of energy. The subtitle here says it all. You can't win, you can only break even. This is basically the universe's ultimate law of conservation. It's telling us, loud and clear, there's no such thing as a free lunch, especially when it comes to energy.
So think of every system as having its own little energy bank account. We call this its internal energy, and we use the letter U for it. This isn't just one type of energy. Oh no, it's the grand total of everything. All the kinetic energy from molecules whizzing around, all the potential energy stored in their chemical bonds, the whole shebang.
So, how do we make a deposit or a withdrawal from this energy account? Well, if we're talking about a closed system, there are really only two ways. First, you have heat, which we call Q. This is all about that random, chaotic jiggling of molecules that we feel as temperature. The second way is work, or W. Now, work is different. It's an organized, directed transfer of energy. Think of a piston pushing up in a straight line, or a muscle contracting to lift something. That's work.
And this brings us right to the heart of the first law, in its famous equation form. Delta U equals Q plus W. What does that mean? It means energy cannot be created or destroyed. It's that simple. Any change in a system's internal energy, the delta U, has to come from somewhere. It's either heat, Q, coming in or out, or work, W, being done on or by the system. That's it. It is a simple, unbreakable budget. Energy just moves around, it doesn't just appear or disappear.
Okay, Section 3. Now, that first law, it's always true. But let's be practical. If you're a chemist working in a lab, trying to measure both heat and the work done can be, well, a real headache. So a very clever shortcut was developed to track energy changes in the real world, and we call it enthalpy. I mean, just think about it for a second. Most chemical reactions aren't happening inside some sealed steel box, right? They're happening in a flask or a beaker, sitting on a lab bench, open to the air. And the pressure from the atmosphere is pretty much constant.
So if your reaction suddenly produces a gas, that gas has to literally push the atmosphere out of the way to make room for itself. That's work. We need an easy way to account for that. And that is exactly where enthalpy comes in. We give it the letter H. Now, the definition is U plus PV, but don't get too hung up on that. Here's the magic part. The change in enthalpy, what we call delta H, just so happens to be exactly equal to the heat that's absorbed or released during a reaction, as long as the pressure is constant. And that's the key. It's the heat flow we can actually measure with a thermometer in the lab. Super useful.
So let's just nail this down, because it's a super important difference. Delta U, the change in energy, that measures the heat change when the volume is held constant, like in a sealed box. But delta H, the change in enthalpy, that measures the heat change when the pressure is held constant. And since most reactions happen out in the open, at constant atmospheric pressure, delta H is the chemist's absolute go-to for figuring out the heat of a reaction.
All right, new section, new big idea. So, we figured out how to measure the heat of a reaction using enthalpy. That's great. But that's not the whole story, is it? Just because a reaction releases heat doesn't mean it will actually happen. To figure out if a process will happen all by itself, we need to introduce a totally new and honestly a very powerful concept: entropy.
Okay, think about this for a sec. You open a bottle of perfume in the corner of a room. What happens? Within a few moments, you can smell it everywhere, right? The scent just spreads out to fill the entire space. You didn't have to do anything to make that happen, it just did. It has a natural direction. We call that spontaneous. But why? Why does it happen?
Now, in thermodynamics, the word spontaneous has a very specific meaning. It means a process that will happen on its own without you constantly needing to push it along. And here's a key point. Spontaneous does not mean fast. Think about iron rusting. That's a spontaneous process for sure, but it can take years. It just means that's the direction nature wants to go in.
So what's behind this natural direction? It's a property called entropy, with the letter S. Now, people often call it a measure of disorder or randomness, which is a good way to start thinking about it. And here is the absolute mind-blowing part. This is the second law of thermodynamics. It says that for any spontaneous process, the total entropy of the entire universe must increase. It's like the universe is on a one-way street headed towards more and more disorder.
Okay, we are so close to the final answer. Let's recap. We have two giant forces driving everything. On one hand, you have the tendency to go to a lower energy state. That's our buddy enthalpy. On the other hand, you have this unstoppable drive to increase disorder, or entropy. So, who wins this cosmic tug of war? Well, it's time to bring in the final boss, the ultimate decider, Gibbs free energy.
Seriously, think of every single process, every chemical reaction as this big tug of war. Pulling on one side of the rope is enthalpy, trying to release heat and get to a lower, more stable energy state. And pulling on the other side is entropy, wanting to create more mess, more disorder, more randomness. So which way does the rope move?
Well, a brilliant scientist named Josiah Willard Gibbs came up with the equation to settle the fight. It's called the Gibbs free energy equation, and what it does is just perfect. It takes the drive for lower energy, R delta H, and it subtracts the drive for disorder, R delta S. But it also multiplies that by temperature, because as it turns out, temperature is the referee in this match.
In the outcome, it's so elegant and simple. You just look at the sign of delta G. If delta G is negative, the reaction is spontaneous. It's a go. If delta G is positive, it's not spontaneous. It's not going to happen on its own. And if delta G happens to be exactly zero, the reaction is at equilibrium. It's perfectly balanced, not wanting to go forwards or backwards. This one number, delta G, tells you everything you need to know. It's our ultimate predictor.
So there you have it. From the smallest chemical reaction in a test tube to the entire cosmos, everything is ruled by this constant battle between lowering energy and increasing disorder. When you see an ice cube melt on your counter, a log burning in a fire, even a star shining in the sky, that's all thermodynamics right there in front of you. So the next time you see anything change, anything at all, just stop and ask yourself, what's winning the tug of war right now? Is it enthalpy or is it entropy? Thanks so much for tuning into this explainer.